Good morning, everyone. It's Friday. Weekend is nigh. I hope you're doing good. If you're still groggy this morning, boy, I sure was, then I hope things go well through your day and that class is entertaining enough. One second down here. So, in brief, this week we've been beginning the first chapter after going over the just course information. The first homework and quiz are live, so do be looking at and working on the homework. I'm planning on us having our first lab next week. If things do not go to my schedule in terms of getting everything planned and prepped and set up in time, I will let you know, but currently the plan is to begin having labs next week. And the homework and quiz are live. That said, I was only just recently made aware that I accidentally set their due date as the wrong day. They are currently, the website says, and they're currently set to, I just haven't had time to fix it this morning. On the website, the due date is listed as Sunday the 7th. My intention is for it to be due on Tuesday the 9th at midnight, so that you can come in that day. We'll have lecture earlier today. You can ask any questions you have about the assignment, and then we do that night. That's usually how I like to do things. The machine defaulted to Sunday for some reason, and I will be fixing that soon. So I was asked about that. I just want to make that clear. Excuse me. And I need water already. Last couple days, it's been very pleasant outside, like a nice kind of warm temperature, jacket not required. This morning it's cold. And apparently, I'm allergic to temperature changes. Because if it shifts too much at once, the barometric pressure shift messes up my sinuses. So basically, every single time of year, be it pollen or pressure, the air is trying to kill me. So I apologize if I sound a little stuffy this morning. Today we're going to continue with Chapter 10. I introduced the idea of thermal expansion last time, so we're going to be looking at the principles and formulas behind that. Before we begin, though, does anybody have any questions? Okay. If you have any at all, and I do mean any, be it about the class or just any science thing that pops into your head, I do encourage you to ask. Thanks to the new Godzilla vs. Kong trailer, my friends have been asking me about what it would be like if those two creatures actually collided. And the physics of it is not good for the human race. Of course, the physics is not in favor of creatures that large existing, period. So the science of kaiju movies is fascinating, and most of it doesn't work.
Wait, Dr. Hopper, I actually do have a question.
Yeah.
So I was thinking about the end of class last other way. We were talking about like thermal expansion. Does our bodies kind of do the same thing, like when your fingers swell and they get hot? Or is that a different thing?
So we are made of matter, therefore our bodies will expand thermally. But the human body and most living creatures are designed to regulate their temperature to some degree. So usually the shift in temperature of a human won't cause too much thermal expansion or contraction if you're cold, just because our internal mechanisms are trying to keep us at a pretty constant temperature, at least on the inside. What would most likely shift most is just your skin, because that's what is feeling the outside temperature. So it would technically happen, just not a lot. If the issue is, say, your ring's not fitting, that's more an issue of the ring's temperature than that of your finger. Excuse me. I do wonder, no wait, your bones are inside of you, so they're at a pretty constant temperature. They're not going to expand much due to thermal input.
I thought it was blood flow.
That would affect it. I know, just due to my own experiences, when I'm overheating, because usually I find being too hot more of an issue than being too cold. When I'm overheating, if I like put specifically my exposed wrists over cold air, that cools my whole body down. Because I've been told, I'm not a biologist, the skin through here is thin enough that the cold, the heat can transfer out of my body through this patch of skin that makes the blood here colder and then circulates to the rest of me. Again though, the inside of you is meant to stay at the same temperature, so that's mostly to do with the temperature your skin is feeling. It would have some effect though. There would be some contraction, and technically speaking, if you feel warmer, if you are overheated, some part of you, probably just the outside, would have expanded more.
Or like your pores. Like that's
Oh,
why
yeah.
yeah, like you're supposed to like heat your face. You wanna like look at your pores. I feel like my fingers do, like my rings don't fit. That's like loosely.
I'm having a little bit of trouble here just because I know there's also biological mechanisms in play. I know it's not just heat that would make your pores expand, and there's lots of things that would make your fingers temporarily increase in size. So there's biological mechanisms I can't speak to personally. But on some level, thermal expansion would count for something, I would say.
That's right, because like when you did like the ball and hook thing, when I thought about it, it's like I wear rings a lot, and like I know when I get really hot, my fingers will swell, but like I'm sure, like you said, it could be also the rings get hot at the same time. But I know my fingers will swell when like I'm outside walking, they'll swell, and I feel like that's when they're hot. So like I kind of thought it's a little bit the same thing. There is obviously biological stuff going on, but I feel like there's maybe a little bit of physics because it's still like hot.
Well, biology is applied chemistry and chemistry is applied physics. So there is physics involved somewhere. There's just a couple layers of science there in human anatomy that I don't have off the top of my head. But it's interesting to think about. My fiance is a nurse, so very frequently we get into conversations about where the two meet. She's training to be a nurse. Anything else before we get started today? It's a very good question. I appreciate it, guys. If you have any more, please do not hesitate to ask. So we left off at the introduction of thermal expansion. Showed you the ring demo. And everything we've been talking about are very good examples of thermal expansion that you probably notice directly on your personhood in your lifetime, but some other places where you would commonly see it include actually liquid thermometers. The way that the thermometers with liquid that rises into the tube works is based on thermal expansion, the liquid inside changes its volume according to its new temperature. When you make a thermometer, you have to calibrate it and mark it just so. You make sure it's at 100 degrees Fahrenheit, and then you mark where the liquid is at that temperature. You calibrate it based on marking it at every other temperature, and then based on the temperature of whatever is in there, it will expand to match its new temperature. So you definitely observe that your whole lives. Since liquids don't really have a length to speak of, liquids tend to, we really only think of liquids expanding in terms of their volume. When something expands, it's going to expand in length, but also in volume at the same scale, because volume is just length in 3 dimensions. But sometimes the problem might only care about one or the other. In terms of length, pretty straightforward. Something will just get longer when it gets hot. And usually in solid objects, you're not going to notice this very much unless you are paying very close attention. When your ring doesn't fit, it's very hard to tell with your naked eye that it is bigger or smaller, even though you can feel it. You know it is, but without a micrometer, you wouldn't know before trying to put it on. In keeping with that, when most things thermally expand, when solids thermally expand, it is usually hard to tell with your naked eye, because solids expand at a slower rate than liquids. Because the particles in a liquid are already further apart, so making them even further apart kind of just increases the process, which is why our thermometers are liquid-based instead of solid-based. So, this is to say that different materials, based on what state of matter they're in, but even what they're made of, can expand at different rates. So, what I'm going to show you now is this very battered, bruised, and scorched object is a bimetallic strip, which means that this long piece of metal here is actually two different pieces of metal stuck together. They're both very thin layers, and combined, this whole device is maybe as thick as your fingernail, but it is made of two different metals on each side. I think one side might be tin and the other side might be nickel. And what I'm going to do here is I'm going to light some more matches, I'm going to heat up this particular object, and because it's made of two different materials on each side is going to expand at a different rate. So even within solid, liquid, or gas, some solids will just expand faster than other solids. And since the two sides are not going to grow at the same rate, that's going to cause it to curl, which is, I think, similar to what causes plants to curl in the direction of the sun, just different growth rates on different sides of the plant. I need to use 2 matches to make sure the effect is fast enough to see. And I'm making sure that it curls up because I find that easier to detect. If it curls down, it could just be gravity. So, this entire motion is due entirely to the thermal expansion. And yesterday I nearly burned my fingertips because with this faceplate on, I can't blow the match out. And if I pull it off, watch very closely, it's going to happen fast. Goes back to normal. This is useful because this is what used to be inside of the thermostats inside of most buildings. The ye olde thermostats that look kind of like a rectangle with a dial on it, you set back and forth, you know, like back in the Pleistocene era. What was inside of those was something very similar to this. The bimetallic strip in that device would move up or down based on its temperature, and the machine inside knew what temperature it was at based on that amount of growth in one direction or the other. And that's how it was able to detect what the temperature was and then make changes based on what you wanted it to be. So this is how thermostats once worked, and different materials expand at different rates. Questions so far? All right. So we've been talking about the principle, what things that affect it. Now let us do some physics and look at all of those things combined into the formulas for these two topics. Ooh, hey. I didn't erase under the board yesterday, so this is all still intact. Except now the rest of it's hard to read, sorry. There we go. So, these are going to be our two formulas for thermal expansion. There's two different versions because, again, when things expand, they do get longer, but the rest of their volume also increases to keep up with it. So, we have two versions of the same formula. They are the same formula. If you look at them, they have the similar terms in the same place, and you do the same math and rearranging on each of them. It's just a question of what variables you are going to plug in to get the desired result. For length expansion, our formula is delta L over initial L. So we have change in length over the initial length of the object will be equal to the temperature change. So how much the length changes is based on how much the temperature changes from a specific value times alpha. This is a new constant called alpha, and this is the coefficient of thermal expansion. Every different material, tin, nickel, concrete, water, etc., has a different coefficient of thermal expansion, like how they all have different coefficients of static and kinetic friction. And because every material has a different one, you will never be expected to remember any of them because there's too dang many, and you will have a table provided for you with those constants on them. So what affects how much something grows is how long it originally was, how much its temperature shifts, and what it's made of. The same factors affect the rate of volume growth. Change in volume equals volume initial. Change in volume over original volume is equal to change in temperature times beta. And beta is also a coefficient of thermal expansion, but it's one related to the volume of that object. So every material has one alpha and one beta for length versus volume expansion. But mercifully, beneficially, for every single material, those two constants are directly related. If you say, know what the alpha of steel is, you multiply it by 3, and that's the beta for steel. So whichever one you're looking at, same principle, same basic formula, it's just a question of what it comes like into it. And the one thing that's always the same across both is delta T. And it's worth noting that because this is delta T, the change in temperature, this is one of the formulas that you can get away with using Celsius or Kelvin in. Because the change in Celsius is the same as the change in Kelvin, since the units are the same size. The only one you can't use here is Fahrenheit. Questions so far? Okay. Now, because the amount that it expands does depend on the original length and the original size, the bigger something is to begin with, the more it is going to grow. Just in terms of the change, like the numerical change in length. If you increase something's temperature by 10%, its size should also increase by 10%, but the bigger something is to start with, the more that number is still going to be. 10% of 1 mile is a lot more than 10% of 1 foot, which becomes an issue in the construction industry when it tends to build very big things. On the hottest day of summer, the Empire State Building might be a foot taller than normal. Civil engineers have two jobs. Civil engineers and architects together, that entire discipline has two jobs. Okay, 3 if you include making drawings. 3 jobs: drawing, factoring in thermal expansion, and making sure all the forces on their building equal 0 at all times. Those last 2 together make sure something doesn't fall over. Buildings have fallen over because some part of it expanded at a different rate than another part, and the whole thing just broke. So, kudos to those engineers, because those are things I certainly didn't know taking an architecture class in high school. Yes?
Wouldn't something expand at a different rate according to how much heat is applied to that certain side? You know what I mean? So like if the sun is over here, then maybe it would bend this way because this side is getting more heat than this side, even though it's the same, like metal. You know?
Right. So even if your building is made out of one constant material all the way throughout, if like just the surrounding terrain makes it such that only one side of it is getting direct sunlight, that side will grow more than the other. And if they're, depending on what it's made of, you will need some system in place to keep that side from growing too much and the whole building from curling over and falling. Granted, again, it's not going to increase by much, but it doesn't take much to knock down a skyscraper if their center of mass is real wonky. Additionally, the different materials in the building will expand at different rates. So if you're using wood, concrete, and steel all together, something might expand more than something else and into another object, and that's how you get cracks in your foundation. And I bring up the original size of the object because The engineering precaution you've probably most likely seen are these little gaps in bridges. Did I mention this one already yesterday? Okay, cool. I'm not repeating myself. When driving over a bridge, have you noticed these weird metal bands that kind of look like teeth, and as you drive over them, the entire bridge just sounds like a kunk, 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 kunk. These teeth are a bridge's thermal expansion precaution. That's it. If you just laid one giant slab of concrete in the ground in the dead of winter, and then you left it alone, it's going to grow some amount in the heat of summer. And if there's not room for it to grow, it's just going to try to push into the ground and not go anywhere. So it's going to buckle up or down and probably break. Yes, we've also lost bridges because of that. So, these teeth, what they do is instead of laying one giant slab of concrete, they lay several slabs of concrete next to each other with these joiners so that you can drive over them mostly smoothly. And the teeth just slide into each other when the concrete gets bigger so that the bridge has the room it needs to do that without falling down.
Wait, so are they naturally like overlapping a little bit, and then as it expands, that's when it like goes more outward, right?
I think, well, the way that I would have built it is such that on the hottest day that you would expect in your area, the teeth would be as close in as they would get. And then in the dead of winter, they would drift slightly apart. But because they are teeth, you always have a surface for your tires to be on because they are jagged. If there was just a hole there, it would be a lot worse than just a good common noise. Yes?
Do wood bridges do the same thing? Or does
All
wood not-
materials do, actually, let me check something real quick, because this is just the next slide. This is a list of those thermal expansion coefficients. Every material has a different one, and tragically, I don't see one for wood on here. This is just the table that the book gives you this chapter. Let me check. Thermal expansion. of
Because
wood.
didn't bridges used to be made out of wood? Or like the big swinging bridges are made out of like wood?
Big swinging bridges?
Yeah.
Like, you know what I'm talking about? Like the ones like there's one at like Grandfather Mountain in North Carolina. They're like just these big like wooden things and you can walk across them. Like, you know, like in movies, like the...
I did like Brussels.
Oh, yes. For a second, I thought this was a bridge that swung and a car went on it.
No. Like ones you can walk on.
Okay.
I mean, I feel like some bridges did used to have some kind of wood in it. I feel like I've seen some kind of story where like bridges have fallen apart because of age.
Yes.
Like way back when, like not recently.
Well, I mean, if it's made of wood, weather's going to make it eventually rot and fall apart. Wood and bugs. Weather and bugs. But for all structures, regardless of what they are made of, because they are going to expand and contract every single season wherever you are in the world, that eventually is why things, even if they're well taken care of, will eventually crack and need repair. Or the bridge just is deemed dead and you have to build another one somewhere else on the river. I couldn't find a quick value for wood, but I do know that wood is mostly water, and water's thermal expansion rate is not insignificant. That said, I would expect it to expand, no wait, water's a liquid, so it might expand more than metal, actually. So wood might get it worse than metal and stone. Depends on how thoroughly you've dried your wood out. Yes?
Is there like a material that like needs extremely high temperatures to expand? So that you could build like something out of that and then you would never need precautions because it's never gonna get that hot, you know?
Right. Well, at least with these numbers that we have here, you would want a smaller constant, because the smaller the number is, the less it would expand. So these are the linear expansion coefficients of 10 different solids. And among this list, the smallest number present is Invar, which is a nickel iron alloy. That does not come up much in one's existence, I feel. But Invar would expand at a rate about 30% slower than lead. So definitely don't make your structures out of lead. A, because expansion, B, because poison. What else is slow on this table? Glass. So glass does not expand nearly as fast as most metals. Steel's pretty slow for metals as compared to, say, these ones up here. But steel is also a metal carbon alloy, so that makes some sense. Thankfully, concrete is pretty slow. Steel's a little slower, so most structures probably use a steel frame and then put concrete over it. So it is possible to try to thermal proof it, but you need to start relying on some very weird materials like Invar and glass.
What's the difference between the two glasses?
I'm assuming that ordinary glass is mostly just melted silicon sand. Pyrex,
I thought that was a brand.
it is a brand. It is a brand, and they named their type of glass after themselves. Or maybe that's the other way around. Lost my train of thought. When I was in grad school, my physics department would drag all of us to job fairs because they cared more about getting us employed than actually teaching us. And Pyrex, because they were science and engineering job fairs, Pyrex was always there. They didn't give out any samples of their containers or anything, but they did have big presentations about our glasses, scientifically designed and engineered to do yada, yada, yada. So it's not pure silicon. There's definitely something else in there to make it chemically different. And the reason for that is, it's going to expand slower than normal glass, which makes it less likely to explode in the oven.
We have just like cooking, they're like bowls you can use in my house, and you use them to like hold stuff and you use them in bowls.
Yeah, wait, sorry, can you repeat that?
No, like they're like bowls at my house. They're like we have like the glass bowl, Pyrex bowls, and you can heat them up with a microwave, and they don't break.
Yes.
They haven't yet, but they could eventually.
Yeah, certain glass materials can break in the oven and the microwave because some part of it might expand at a different rate than others, or it might expand too much, or there might be an air bubble inside that expands at a different rate and causes a rupture. So the Pyrex glass is just that company modifying their formula to reduce that as most as they can. Yes.
Over time, does the coefficient change? Like, oh, maybe it's worn out, so it doesn't have as much thermal capacity.
Well, if the material and chemical composition is exactly the same, it shouldn't. But over time, as things wear out, what's likely happening is there's just cracks forming that keep progressively getting worse. It's not that the material changes, it's just the configuration of the physical object changes. But it is possible for something's chemistry to alter over time, depending on what it was originally. I know metal will rust and break down eventually. That would definitely change the rate of, the rust would have a different rate than the base metal. So this table is handy. It exists in your notes. You are allowed to use it whenever these problems come up. In general, if you are told what something is made of in a question, that is your invitation to consult this chart. And if it's not in this chart, I'll try my best to make sure it is provided to you in the question. Either the question will tell you the material and you can get this number, or the question will be, you have the information to solve for it, and then you figure out what it's made of. And just one thing that's worth noting, this column is linear expansions of solids, this column is volume expansion of fluids, but because of the rule beta equals 3 alpha, you can use one to find the other. But notice, volumes expand at a faster rate than solids. And I know that to the -4 is, you'd think a smaller, 4 is a smaller number than 6, but this is 10 to the -4, which means these are bigger numbers. So, that's a lot of talking and a lot of information. Let's start to utilize it. We have an aluminum pipe, and and it is a very long piece of aluminum because it is 18.7 meters at your starting temperature. Now, standard tactics for working physics questions are going to be the same as they've always been. You want to make sure you know, list out what you know, what you don't know, figure out what formulas you want to use that information in. So, things that we know, we have an aluminum object, which means we will eventually need some constant related to aluminum. We know temperature initial is going to be 21.1 degrees Celsius. At that temperature, length initial is going to be 18.700 meters. My zeros look like twos sometimes. I'm gonna work on that, it's all right. And we are asked to find final length. If you don't know that, we're going to find it when the final temperature is 29.4 degrees Celsius. So, these are the three numbers the problem gives us. It also tells us the identity of the material. Because we're working with lengths, we're going to go to our table and consult what the coefficient of linear expansion is for aluminum. It's the first one on that left side. It's going to be 24 times 10 to the negative sixth. I am going to write that on the board. I'm just going to tap back a little bit next to my computer. And this number does technically have a unit so that the equation proceeds as normal. That unit is technically 1 over degrees Celsius. And that's so that it cancels out the temperature unit and leaves you with your length units. So, these are the things we know and the one thing that we don't know but want. So, what's our formula? Which one should we use with this information? Sorry, a little louder. Very good. And can you just repeat it out loud for me? It might be, yes, it might be annoying, but I find saying it out loud helps remembering.
Something like delta L.
Yep.
Over L equals alpha delta T.
Very good. Thank you very much. So that's our formula, and we can start plugging things in, start proceeding.
Wait, really quick. If they gave you your temperature in Kelvin, can you still use the alpha and Celsius because it's proportional?
Yes, you can.
Everything but Fahrenheit.
Yes. That said, make sure that the two temperatures you plug in for delta match. Because if they gave you, if for some reason it said it starts at this Celsius and it ends at this Kelvin, those won't be compatible. So make sure these match, and then you'll be fine. As long as it's delta T, Kelvin or Celsius should both apply. So, we start plugging things in. Our first term is delta L. Delta anything always means final minus initial. So that's going to be length final minus length initial over length initial is equal to alpha times delta T. Again, delta is going to be final minus initial. It's going to be 29.4 minus 21.1. That's going to give us a positive delta T, which makes sense because it got warmer. And we only have one unknown term left, so we are good to begin plugging in and solving, rearranging and solving. So, how's our delta, how is our L final looking?
Like almost the same.
Almost the same, yes, but not technically the same.
18.702.
I got 37.
As did I. But my original notes did also say 18.702. So I'm,
Does that like super matter?
not to me, it might matter to WebAssign. I'm just going to round it off there for right now.
Also, like remember one time, like significant digits?
It does, yes.
So like, wouldn't the answer be like 18.7? And then it's like. it
Well,
kind of-
notice that the original number comes to here,
But
which
like,
means we have 5 sig figs.
but your temperature has.
Oh, yes, yes,
Yeah.
you're right. Good point. Also, our alpha only is 2, so that's frustrating. Okay, so when I multiply this number by these, I've got 0.003725. If we only have 2 sig figs from this number, I'd call that 0.0037, the 3 and the 7 being the 2 sig figs. And when you would add that number to this, I would keep both of them. I would say that this should be your final answer based on sig figs.
Okay, I thought you don't use sig figs from constants. Because like, there's.
Oh, no, you're right. Ah, jeez.
Like this on a test, would it super matter? Because I know WebAssign would be weird. But like,
WebAssign would be weird. It would not super matter to me,
Okay.
because you've mathematically gotten to approximately the answer I was expecting, which is to say it didn't expand much. It did not expand much, yes.
Is there any way that you can work that out, like the algebra form?
Oh, sure. I always misplace my erasers, problem I have. And because I misplace them, my hand becomes the eraser, which means I'm covered in dry erase dust all day.
I just know that.
Oh, man, I feel lazy. Thank you, though. That'll help me later. Thank you very much. So, LF minus 0 equals 27 times 10 to the negative 6 times, I'm just going to go ahead and find that temperature difference, so I just don't keep writing it. It's 8.3 times 8.700. That's going to give us LF minus 18.700 equals 0.0037. And then we add this to the other side, we should get 18.70373. If we're not looking about sig figs too much.
What kind of work do you want for tests? Like, do you want that, or can I have gone from degree to answer? Or like, you know?
You are always better off showing me more, because if there's a mistake, it'll help me, it'll help show me that more work will show me that you do know what you were doing, and it'll help me find where the mistake was. That said, I could, from this, go to my calculator and get to the final answer in one step, just because that's just how my brain works. but proper form might be better off writing more things. It's ultimately going to be up to you whether you want to, how much you feel the need to write down. I'd say from here to answer this, getting to this point is most of your points, but the more work you show, statistically you'll be better off if there's a problem. It's going to come down to you guys, exactly how much you choose to write down in the moment. Yes?
Speaking of sig figs for a lab, do we need to have significant fingers?
At least for labs, I will try to make sure that you measure to the appropriate amount of sig figs for each tool, which is to say you always estimate one pass where the tool tells you for certain. I'm going to try to encourage that on labs, but I don't think I will. I'm not too particular about sig figs on tests, just because the computer already is, frankly. Okay. So, 18.7 meters is very long. That is about 2 stories of a building. No, wait. Sorry, I'm getting my conversions mixed up. 18.7 times 3.3. Okay, that's about 62 feet. It's about 21 yards. So, that's a long piece of metal, and it didn't grow that much. Like, it grew a couple of millimeters. So you're not gonna, again, you won't notice that unless you are looking for it. This mostly becomes an issue, come on, Peter, good job. This is mostly an issue with things that are already big. Because if you're laying out lines and miles of track like this, if it doesn't have room to grow, it's going to start buckling wherever it can make space. And if a train hit that at speed, things would go poorly for everyone involved. I think train tracks have spacers to account for this every so often. They aren't usually solid pieces of metal, precisely because you get nonsense like this. Thank you very much. Okay.
Did we learn this information through like trial and error, or did like someone find it out like before bad things happened?
You know, I don't know when in human history we actually realized this was happening.
Like, I'm just curious, like, because I've never seen it. I mean, I haven't been alive to see like trains like actually, you know, function like what it used to. But like, I've never seen a train track buckle like that. Doesn't mean they didn't.
Which hopefully means that all the tracks you've seen were built right.
Right.
But see, like, even back in the day, they had like wooden bridges that they went over with like buildings and stuff like that.
Yes. So I do imagine a lot of this, like, some of the dates I'm getting at this cursory search put the discovery of this principle in the mid-1800s, which puts a couple millennia of human history ahead of that, where we didn't have the math for it, and things would definitely break. And yes, exactly. Hang on, let me check the invention of the train. Well, yep, trains existed before thermal expansion math did, so something bad might have happened there. Not this, because that's a more modern rail car, and there's electricity going on in the background, but yeah, I foresee something bad happening there. Also, the thermal expansion would just be weird in the steam train, because the entire steam compartment would get really hot and expand more than every other part of the train. Excuse me. Very interesting question, though, because I had not thought about the order of events there. Any other questions? Okay. The next thing I have for us is a very similar example
So I think we're gonna wait to start that next time. It's sort of cold open from over the weekend, actually. I think we already talked about this though. You guys asked a very good, you can go ahead and start backing up. I just like saying things that are going on in case if you hadn't heard already comes out. I think we already mentioned, because we're asking some good questions, that as you heat something up, 9.9 times out of 10, it's going to increase in size. Because the mass doesn't change, there's still the same number of atoms just farther apart. That means that the density changes as you increase in temperature. So this is a density versus temperature graph. And if you're looking at the solid object, its density is just going to drop and drop as it heats until eventually it melts. And melting is basically one big giant density shift all at once. Once it's shifted into liquid, then it's going to keep becoming less dense. And this density shift is one of the things that creates air currents on planet Earth. Because hot air is less dense than cold air, which is why it rises. This creates a convection currents in your oven, which allows your food to cook. Also when you're boiling water for noodles, also this causes most of the weather. Though there's kind of one weird exception, and it's that water expands when it freezes. I think you guys asked about this, and that's one of the few weird times it happens entirely because solid water takes on this specific lattice shape, which occupies more volume than the liquid. But it's a good thing this happens, even if it's weird, even if it causes soda cans to burst in the freezer, because if this didn't happen, life on Earth wouldn't be possible. This glitch in the matrix is important because this makes ice less dense than water, which makes it float in water. If ice did not float in water, it would all sink, which means the bottom of the ocean would become one continuously growing giant piece of ice, which would continuously keep getting bigger, driving up the ocean levels until the entire planet was a snowball and there was no liquid water left. So this planet is habitable because this happens. So this glitch is on purpose. Everything else though, barring a few other crystal things, always expand when warm and contract when cold. All right. Thank you all. And yes.
Will you be posting the other barrel box as well?
Yes, I will. As
We finish.
yes, I want to try to work ahead to put some of them there, but I put work into check them to make sure it is as close to the draft I'm going to be using as possible.
Yes, sir.
But those are goals. You hope you have a wonderful weekend and the first week back for you. Rest well, be working on your homework. Again, normally we'll be doing one a week, so normally we'll be doing this coming Tuesday, just not this time because mercy. But do be working on it, and